At the heart of the Milky Way, hidden behind thick clouds of dust and tightly packed stars, there is something we cannot see directly, yet it outweighs millions of suns. It does not shine like a star, and it does not glow like a nebula. Its presence is revealed only through its gravity, shaping the motion of everything around it. This object is known as Sagittarius A star, the supermassive black hole that sits at the center of our galaxy. Unlike the brilliant black holes that power distant quasars and active galaxies, Sagittarius A star is unusually quiet. It does not blaze across the cosmos or flood its surroundings with radiation. For long stretches of time, it barely whispers. Yet beneath this calm exterior lies an environment of extreme gravity, tangled magnetic fields, and matter moving at incredible speeds. Even in silence, it is one of the most powerful objects in the Milky Way. For much of human history, the center of our galaxy was unreachable. Early astronomers could chart the motions of planets, map constellations, and trace the broad band of the Milky Way across the night sky. But when they looked toward its brightest region, in the direction of the constellation Sagittarius, their view seemed to fade into confusion. Light from that part of the sky appeared smeared and broken, interrupted by dark lanes and crowded with overlapping stars. Something was blocking the view. That barrier was not empty space, but dust. Between the stars of the Milky Way drift vast clouds of interstellar material, made of tiny grains of carbon, ice, and silicate rock. These particles are small, but they are spread across enormous distances. Visible light struggles to pass through them. It is scattered, absorbed, and dimmed long before it can reach Earth. Nowhere is this effect stronger than toward the galactic center, where dust and stars are packed together in extraordinary density. What we now call the galactic bulge lies in this direction. It is a swollen central region filled with old stars moving in all directions, layered together so closely that their light blends into a soft glow. Alongside them float thick veins of dust that carve dark shapes through the brightness. From Earth, this combination created the illusion of a glowing cloud crossed by shadow. For centuries, it concealed the true heart of the galaxy. Early attempts to understand the Milky Way were shaped by this limitation. Astronomers in the 18th and 19th centuries tried to map the galaxy by counting stars in different directions. Where they saw many stars, they assumed the galaxy extended far. Where they saw few, they assumed its edge was near. Unaware of interstellar dust, they did not realize that their maps were being shaped by obscuration rather than structure. In some models, the Sun even appeared to sit near the center of the galaxy, simply because the true center was hidden from view. The problem was not solved until astronomers learned to look with new kinds of light. Visible light, the narrow slice of the spectrum our eyes can see, is only one way to explore the universe. Other forms of light, such as infrared and radio waves, can pass through dust far more easily. They carry information from regions that appear dark in optical telescopes. As instruments sensitive to these wavelengths were developed in the 20th century, the Milky Way began to reveal its hidden layers. Infrared observations showed stars buried deep within the galactic bulge. Radio telescopes detected energy coming from places where no visible source could be found. The center of the galaxy, long silent to our eyes, was beginning to speak. One of the first clues came unexpectedly. In the early 1930s, an engineer named Karl Jansky was investigating sources of interference in long-distance radio communication. While studying static signals with a rotating antenna, he noticed a faint hiss that appeared and disappeared with a regular rhythm. It did not follow the cycle of the sun. Instead, it returned slightly earlier each day, tracking the rotation of the Earth relative to the stars. Jansky eventually traced this signal to the direction of the Milky Way's center. For the first time, radio waves were detected coming from beyond the solar system. The discovery was accidental and, at the time, not fully appreciated. Yet it marked the birth of radio astronomy and opened a new window onto the universe. In the years that followed, radio astronomers began to map the sky in this invisible light. Among the strongest sources they found was a compact region in the constellation Sagittarius. It was labeled Sagittarius A, the first major radio source identified in that area of the sky. As instruments improved, this source was revealed to be complex, containing several components. At its very center was a remarkably bright and compact point. It became known as Sagittarius A star. Even then, its nature was unclear. It emitted radio waves, but it did not resemble a star, a nebula, or a supernova remnant. What drew increasing attention was the behavior of the stars around it. They moved fast, following tight paths as if circling an enormous, unseen mass. The center of the Milky Way was not empty. It was dominated by something dense, dark, and extraordinarily powerful. That truth would only become clear once astronomers learned to see through the dust completely, and once they began to watch the stars themselves dance around an invisible anchor. As infrared technology improved, the galactic center slowly emerged from the shadows. Infrared light, with its longer wavelengths, could slip between dust grains that blocked visible light, carrying information from regions that had been hidden for millennia. When astronomers pointed these new instruments toward Sagittarius, the darkness dissolved into structure. Where optical telescopes had shown only smears and voids, infrared images revealed dense clusters of stars packed tightly together, all moving within a confined volume of space. Observing this region was still extremely difficult. Earth's atmosphere absorbs much of the infrared light arriving from space and adds its own heat to the signal, creating noise that can overwhelm faint details. To reduce these effects, astronomers built observatories on high, dry mountaintops where the air is thin and stable. Places like Mauna Kea in Hawaii and the Atacama Desert in Chile became gateways to the hidden center of the galaxy. From these sites, astronomers began to track individual stars near Sagittarius, a star with unprecedented precision. They were not drifting slowly, as stars do in the outer regions of the Milky Way. They were racing. Some completed full orbits in only a few decades, others in even less time. These motions could not be explained by the gravity of visible stars alone. Something extremely massive was holding them in place. By following these stars year after year, astronomers could reconstruct their orbits in detail. One star in particular, known as S2, traced a long, elongated path that brought it very close to the unseen center before flinging it back out again. Its speed increased dramatically at closest approach, reaching several thousand kilometers per second. Only an enormous concentration of mass could produce such an effect. From these measurements, the mass of the central object could be calculated. The answer was staggering. Roughly 4 million times the mass of the Sun, confined within a region smaller than our solar system. There was no known object other than a supermassive black hole that could account for this combination of mass and compactness. The case for Sagittarius A star as a black hole became overwhelming. At the same time, radio observations continued to sharpen. Techniques such as very long baseline interferometry linked radio dishes across continents, creating a virtual telescope as large as Earth itself. This allowed astronomers to measure the apparent size of Sagittarius A star with extraordinary accuracy. Even at a distance of about 26,000 light-years, its emission region appeared incredibly small. Whatever lay at the center of the Milky Way was both massive and tightly confined. Yet despite all this evidence, the black hole itself remained unseen. Black holes do not emit light directly. Instead, they reveal themselves through their influence on surrounding matter and through the bending of spacetime itself. To understand what Sagittarius A star truly was, astronomers needed to study not just its mass, but its environment. Not all black holes are the same. The smallest form when massive stars collapse at the end of their lives, leaving behind stellar mass black holes only a few times heavier than the Sun. These objects are scattered throughout the galaxy and are often detected when they pull gas from a nearby companion star, heating it until it shines in X-rays. Larger still are intermediate mass black holes, thought to weigh hundreds or thousands of solar masses. Their origins are uncertain, and their existence is difficult to confirm, but they may form in dense star clusters or through repeated mergers of smaller black holes. They are rare, elusive, and may represent a missing link in black hole growth. Sagittarius A star belongs to the largest class of all. Supermassive black holes dominate the centers of galaxies, weighing millions or even billions of times more than the Sun. Nearly every large galaxy appears to host one. These giants are not simply passive occupants. They are deeply connected to the formation and evolution of their galaxies, influencing the movement of stars, the flow of gas, and the rate at which new stars are born. Compared to many of its counterparts, Sagittarius A star is unusually quiet. Some supermassive black holes consume vast amounts of material and blaze with energy, becoming quasars visible across the universe. Sagittarius A star, by contrast, feeds slowly. Only small amounts of gas and dust drift inward, producing faint emissions in radio, infrared, and X-ray light. This low activity makes it harder to study in some ways, but it also creates a relatively clean laboratory for understanding black hole physics without the chaos of extreme feeding. Despite its calm appearance, the region near Sagittarius A star is anything but gentle. Matter that approaches too closely is accelerated to extreme speeds. Magnetic fields twist and tangle, guiding streams of charged particles. Space and time themselves are warped by gravity so intense that familiar rules begin to bend. Every so often, the quiet breaks. Sudden flares of infrared and X-ray light erupt near the black hole, brightening the region for minutes or hours before fading again. These bursts may be caused by clumps of gas falling inward, or by magnetic fields snapping and reconnecting, releasing stored energy in an instant. They offer brief glimpses of processes occurring just outside the event horizon. Evidence suggests that Sagittarius A star was not always so subdued. Reflections of past X-ray activity can still be seen echoing through nearby clouds of gas, hinting that centuries ago the black hole may have been far brighter than it is today. The occasional flare we see now may be a faint reminder of a more active past, or a hint of activity yet to come. For now, Sagittarius A star remains a quiet giant, shaping the heart of the Milky Way through gravity alone. But even in silence, it continues to teach us about the most extreme environments in the universe, inviting us to look closer, deeper, and with ever more patient eyes. To understand what happens so close to Sagittarius A star, astronomers must think not only about gravity, but about magnetism. Near the event horizon, the space around the black hole is filled with hot, electrically charged gas known as plasma. As this plasma moves, it carries magnetic fields with it, stretching and twisting them into complex shapes. These fields are invisible, yet they can rival gravity in shaping how matter behaves. For a long time, magnetic fields near black holes were thought to be secondary, little more than background features. Recent observations have changed that view. Data from the Event Horizon Telescope has revealed patterns of polarized light around Sagittarius A star, showing that strong magnetic fields thread the region just outside the event horizon. They are not random. They show signs of structure and alignment, suggesting that magnetism plays a central role in controlling how material flows inward. Gravity pulls matter toward the black hole relentlessly, but magnetic fields can resist that pull. When field lines become tightly wound, they can act like barriers, holding gas in orbit or redirecting it away from the center. This may help explain why Sagittarius A star consumes so little material. Much of the gas that drifts close is heated and stirred by magnetic turbulence, then pushed back outward rather than swallowed. The black hole is surrounded by fuel, yet remains underfed. Magnetic fields also store energy. When the twisted lines suddenly snap and reconnect, that energy can be released in violent bursts. Near Sagittarius A star, such reconnection events are a leading explanation for the sudden flares seen in infrared and X-ray light. Particles are accelerated to near light speed, radiating intensely for a brief moment before the system settles again into calm. The balance between gravity and magnetism creates an environment that is both stable and unstable at the same time. Stable enough to avoid constant outbursts, yet unstable enough to produce occasional flashes of activity. This delicate equilibrium makes Sagittarius A star an ideal place to study how black holes behave when they are neither dormant nor fully active. At the center of this system lies a boundary that defines the black hole itself. This boundary is known as the Schwarzschild radius, named after the physicist Carl Schwarzschild, who first described it while solving Einstein's equations of general relativity. The Schwarzschild radius marks the size of the event horizon. Once anything crosses this boundary, it can never return or send information back to the outside universe. For Sagittarius A star, the Schwarzschild radius is surprisingly small given its mass. Although the black hole contains about 4 million solar masses, its event horizon spans only a few million kilometers. All that mass is compressed into a region only a little larger than the orbit of Mercury. Beyond this point, space itself is falling inward faster than light can escape. The event horizon is not a solid surface. It is a point of no return defined by geometry rather than matter. From far away, it appears as a simple mathematical boundary. Up close, the effects become extreme. Time slows relative to the outside universe. Light is stretched and reddened. Paths that once led outward curve back inward, sealing off the interior forever. When the Event Horizon Telescope imaged Sagittarius A star, it did not capture the black hole directly. Instead, it revealed a dark shadow surrounded by a glowing ring of radio emission. This ring is formed by light from hot plasma orbiting close to the event horizon, bent by gravity into a circular shape. The shadow at the center is slightly larger than the event horizon itself, a silhouette carved by the bending and capture of light. Imaging this structure was one of the greatest technical challenges in modern astronomy. From Earth, the apparent size of Sagittarius A star is extraordinarily small, comparable to seeing an object the size of a coin on the surface of the Moon. To achieve the necessary resolution, radio telescopes across the planet were linked together, synchronizing their observations with atomic clocks, accurate to within fractions of a second over millions of years. Even then, Sagittarius A star proved difficult. The material around it changes rapidly, reshaping the glow from minute to minute. Unlike the black hole in the galaxy Messier 87, whose surroundings evolve slowly, Sagittarius A star is restless. Capturing its image required combining data from many moments and extracting the features that remained consistent through the turbulence. The result was a confirmation of theory. The size and shape of the shadow matched the predictions of general relativity with remarkable accuracy. Yet the image also raised new questions. It showed where the boundary lies, but not how matter behaves from moment to moment. It revealed the outline, but not the full story. Outside the event horizon, gravity bends light in another subtle way. Stars and clouds passing near Sagittarius A can act as lenses, warping the light from objects behind them. In rare alignments, this gravitational lensing can briefly magnify distant sources or distort their shapes. Even the black hole itself bends light from background stars, offering another way to measure its mass and influence. These effects are difficult to capture and fleeting, but they provide valuable clues. Light that takes multiple paths around the black hole can arrive at different times, creating echoes that reveal the geometry of space-time near the center. In this way, gravity itself becomes a tool for observation, focusing and reshaping our view. Much of what we know about Sagittarius A has also depended on a technology that corrects for distortions much closer to home. Earth's atmosphere blurs incoming light, causing stars to shimmer and shift. Adaptive optics systems counteract this by measuring atmospheric distortion in real time and reshaping telescope mirrors to cancel it out. With this technology, ground-based telescopes can achieve clarity once possible only from space. Adaptive optics transformed our view of the galactic center. Individual stars snapped into focus. Their orbits could be traced with extraordinary precision. Subtle effects predicted by general relativity, such as the gravitational redshift of starlight near the black hole, became measurable. Without this correction, the stellar dance around Sagittarius A would remain a blur. Together, these tools have turned the once hidden center of the Milky Way into one of the best-studied regions of extreme gravity in the universe. And yet, even with all this progress, the deepest mysteries remain just beyond reach, sealed behind a boundary we can outline but never cross. As observations of Sagittarius A grew more precise, astronomers began to ask deeper questions about its nature. The evidence strongly supports the idea that it is a supermassive black hole, but science advances by testing even its most successful explanations. For an object this extreme, alternative ideas have been explored, not because the black hole model is weak, but because understanding why it works so well is just as important as considering what could replace it. One possibility sometimes raised is that the central mass could be a dense cluster of dark matter. Dark matter does not emit or absorb light, and its presence is known only through gravity. In theory, a large concentration of it could pull stars into fast orbits without producing visible radiation. The difficulty lies in compactness. Dark matter, as we understand it, does not easily lose energy or collapse into a tightly packed object. Observations show that the mass at the galactic center is confined to an extraordinarily small region, far denser than any known dark matter structure could form. More exotic ideas have also been proposed. One is the boson star, a hypothetical object made from ultra-light particles that obey different quantum rules than ordinary matter. Such an object could be massive and compact without forming an event horizon. From a distance, its gravitational effects might closely resemble those of a black hole. At current resolution, even its shadow could look similar. The difference would lie in subtle behavior near the center, where infalling matter might slow or emit light differently rather than disappearing entirely. Another theoretical alternative is the gravastar, short for gravitational vacuum star. In this model, the collapse of matter is halted just before an event horizon forms, replaced by a thin shell of exotic energy surrounding a strange interior state. From the outside, a gravastar would behave almost exactly like a black hole. The challenge is observational. Any surface, no matter how extreme, should eventually reveal itself through bursts of radiation when matter impacts it. No such signals have been detected near Sagittarius A. there are even more speculative ideas. In some versions of string theory, black holes are described as fuzzballs, tangled configurations of fundamental strings rather than empty regions surrounding a singularity. In this view, there is no clear boundary where space ends, only an extremely complex structure that mimics the external appearance of a black hole. Other proposals imagine black holes as gateways, linking distant regions of space or even separate universes through wormhole-like structures. All of these ideas share a common problem. They must reproduce not only the mass and compactness of Sagittarius A star, but also the precise motion of stars, the shape of the shadow, and the behavior of matter near the center. So far, every observation aligns with the predictions of a black hole described by general relativity. Alternatives remain mathematically interesting, but observationally unsupported. Beyond questions of identity lies the question of influence. How much has Sagittarius A star shaped the Milky Way itself? The galaxy we see today is a spiral of stars and gas, extending across hundreds of thousands of light-years, yet its inner regions tell a different story. Near the center, stars move in complex patterns, forming a dense bulge and a long bar structure that channels material inward. In the early history of the Milky Way, billions of years ago, the galaxy was far less orderly. Gas clouds collided, star formation was intense, and smaller proto-galaxies merged into the growing system. During this chaotic period, the central black hole likely grew rapidly, feeding on inflowing matter and possibly merging with other black holes brought in by collisions. When a supermassive black hole is actively feeding, it can influence its surroundings far beyond its immediate reach. Energy released by inflating matter can heat gas, drive winds, and in extreme cases launch jets that extend thousands of light-years. These processes can suppress star formation in some regions while triggering it in others. They act as a form of feedback, regulating how galaxies grow. The Milky Way shows signs that Sagittarius A star may have been more active in the past. Vast structures known as the Fermi bubbles rise above and below the galactic plane, emitting high-energy radiation. One possible explanation is that they are relics of a powerful outburst from the central black hole millions of years ago, when it briefly behaved more like an active galactic nucleus. Today, Sagittarius A star exerts its influence more subtly. Its gravity dominates the motion of stars in the inner parsecs, helping shape the central cluster. The combined mass of the black hole and the surrounding stars contributes to the stability of the galactic bar, which in turn affects how gas flows through the inner galaxy. In this way, even a quiet black hole can play a long-term role in galactic evolution. Far from the center, in the spiral arms where the Sun resides, the black hole's direct gravitational influence is negligible. The motion of stars there is governed by the overall mass of the galaxy and by density waves that shape the spiral pattern. Sagittarius A star does not dictate the structure of the outer Milky Way, but it may have helped define the character of its core. Understanding this balance is one of the central challenges of modern astrophysics. Black holes and galaxies appear to grow together, their masses linked in ways that suggest a deep connection. Whether the black hole drives the galaxy drives the black hole, or both evolve in tandem remains an open question. Looking ahead, astronomers are preparing a new generation of instruments designed to probe Sagittarius A star in even greater detail. The Event Horizon Telescope is expanding, with new stations planned to fill gaps in coverage and sharpen its vision. Observations at multiple wavelengths will reveal how different layers of plasma behave near the event horizon. There is also growing interest in observing the black hole in motion. With enough data, it may be possible to create time-resolved images, capturing the flow of matter as it orbits and flares. Instead of a single static picture, we could watch the environment change, frame by frame, revealing the dynamics of extreme gravity in action. Beyond electromagnetic light lies another frontier. Gravitational waves offer a way to sense massive events without relying on photons at all. Sagittarius A star itself is stable and quiet, but if a smaller black hole or dense star were to spiral inward, it would produce slow, powerful ripples in spacetime. Future space-based detectors such as the Laser Interferometer Space Antenna are designed to hear these signals, potentially allowing us to listen to matter falling into our galaxy's central black hole long before the green. Final plunge. Such observations would provide unparalleled tests of general relativity and offer precise measurements of mass and spin. They would also give us a new way to study the region just outside the event horizon, free from the distortions of dust and gas. Even with all this promise, the interior of the black hole remains forever hidden. No telescope, no detector, no wave can carry information back once it crosses the event horizon. The heart of Sagittarius A star is sealed from the rest of the universe. We can trace its outline, measure its influence, and model its behavior, but its inner reality belongs to a realm beyond observation. And yet, by studying the edges of that boundary with ever greater care, we continue to learn not only about black holes, but about the fundamental nature of space, time, and gravity itself. The story of Sagittarius A star does not end with what we can see today. Its future, and the future of the Milky Way itself, are written on timescales far longer than any human history. To understand where this black hole is headed, astronomers look beyond our galaxy and study the lives of others, catching glimpses of what may one day unfold at our own center. Galaxies are not isolated islands. Over billions of years, they drift, collide, and merge, drawn together by gravity. The Milky Way is no exception. It is moving toward its nearest large neighbor, the Andromeda Galaxy, at a speed of roughly 100 kilometers per second. Though that motion seems fast, the distance between them is immense. The encounter will not happen for about 4 billion years. When the Milky Way and Andromeda meet, their stars will mostly pass by one another without direct collisions. Space between stars is vast, even in the crowded cores of galaxies. The real transformation will come from gravity reshaping their structures. Spiral arms will stretch and distort. Gas clouds will collide and compress. New waves of star formation will ignite as material is stirred and redistributed. At the center of this slow-motion encounter will be two supermassive black holes. Sagittarius A star in the Milky Way and the black hole at the heart of Andromeda will begin a long gravitational dance. As their host galaxies merge, the two black holes will sink toward the newly formed center through a process known as dynamical friction, losing energy as they pass through dense fields of stars and dark matter. Over tens of millions of years, the pair will draw closer, orbiting one another at ever-shrinking distances. As they do, they will emit gravitational waves, ripples in spacetime that carry energy away from the system. In the final stages, these waves will grow stronger and more rapid, marking one of the most powerful events the universe can produce. Eventually, the two black holes will merge into a single, larger one. The resulting black hole could be tens of millions of times more massive than the Sun. Its spin would reflect the combined histories of both galaxies, shaped by the directions and speeds at which the two giants collided. For a time, the merged core could blaze with activity as vast amounts of gas fall inward, potentially outshining the combined starlight of the surrounding galaxy. For any world still orbiting stars within the merged system, the effects would vary with distance. Near the core, intense radiation could strip atmospheres and sterilize surfaces. Farther out, the changes might be more subtle. Skies would shift as constellations rearranged. The soft band of the Milky Way would be replaced by a more diffuse glow, marking the transformation of a spiral galaxy into an elliptical one. Long before this collision, the fate of Earth will likely be sealed by more local events. Our Sun is slowly growing brighter as it ages. In another 1 to 2 billion years, increased solar radiation may trigger a runaway greenhouse effect, evaporating the oceans and ending surface life. In about 5 billion years, the Sun will exhaust its core fuel and expand into a red giant, potentially engulfing the inner planets. By the time Sagittarius A star meets its counterpart from Andromeda, Earth may already be a silent remnant, orbiting a white dwarf or gone entirely. If intelligent life still exists anywhere in the merged galaxy, it may be far from the core, watching these events from a safe distance, or it may have spread beyond the confines of any single galaxy. Yet the significance of Sagittarius A star extends beyond any single future event. It represents a point where our understanding of the universe is tested to its limits. Near its event horizon, gravity is strong enough to warp space-time dramatically. Magnetic fields twist and snap. Matter behaves in ways that challenge our models. Every observation made there is a probe into physics under conditions that cannot be recreated on Earth. In the coming decades, new tools will sharpen that probe. Expanded networks of radio telescopes will refine images of the black hole shadow. Polarization studies will reveal the structure of magnetic fields in unprecedented detail. Space-based observatories will listen for the low-frequency hum of gravitational waves from objects spiraling into the central mass. There is even the possibility that future instruments could capture changes in real time, turning static images into moving portraits of plasma orbiting at the edge of darkness. Such observations would not just confirm existing theories. They could reveal surprises, showing us where our understanding breaks down and pointing the way toward new physics. For now, Sagittarius A star remains unseen, known only through its influence. It anchors the Milky Way, holding the motions of countless stars in its grasp. It stands as a reminder that the universe contains regions where the familiar gives way to the extreme, and where curiosity must be guided by patience. By tracing its shadow, listening to its flares, and watching the stars that circle it, we have learned to study something that cannot be observed directly. In doing so, we have turned absence into evidence, darkness into data. And at the heart of that effort lies a simple realization. Even the quietest black hole has a story to tell, if we learn how to listen. Beyond the grand future of galaxy mergers, there is another frontier where Sagittarius A star may one day speak to us in an entirely different language. This language is not made of light, but of motion itself. Gravitational waves carry information through the universe, not by shining, but by gently stretching and squeezing space as they pass. They are among the most direct messengers of extreme gravity we have. A stable, isolated black hole like Sagittarius A star does not produce strong gravitational waves on its own. Its mass is enormous, but without change, there is no ripple. For gravitational waves to form, something dynamic must occur. A collision, a sudden disruption, or a slow spiral inward of another massive object. The most promising of these scenarios is known as an extreme mass ratio in spiral. In such an event, a much smaller object, perhaps a stellar mass black hole or a neutron star, becomes trapped by the gravity of Sagittarius A star. Over thousands or even millions of years, it spirals inward, tracing complex paths through warped spacetime. Each orbit sends out a faint but persistent signal. Near the end, as the smaller object approaches the event horizon, those signals grow stronger and more intricate, encoding precise information about the black hole's mass, spin, and the shape of space-time around it. These signals are too slow and low in frequency for ground-based detectors like LIGO and Virgo, which are tuned to the sharp chirps of stellar mass mergers. Instead, they will be targets for future space-based observatories. The Laser Interferometer space antenna, planned for the coming decades, is designed specifically to detect these long, deep gravitational murmurs. If such an inspiral were detected at the center of the Milky Way, it would be a scientific treasure. Astronomers could follow the signal for years, mapping the geometry of space-time around Sagittarius A star with extraordinary precision. No dust, no gas, and no magnetic field could obscure the measurement. Gravitational waves pass through matter almost untouched, offering a clean view of gravity itself. These observations could test general relativity in its most extreme regime. Einstein's theory has passed every test so far, but conditions near a supermassive black hole push it to its limits. Any deviation in the waveform could hint at new physics, perhaps pointing toward a deeper theory that unites gravity with quantum mechanics. While gravitational waves reveal motion, another emerging tool may reveal orientation. The spin of Sagittarius A star remains uncertain. Spin affects how space-time is dragged around the black hole, how matter orbits, and how energy can be extracted from rotation. One of the most promising ways to measure spin is through X-ray polarimetry. When matter falls toward a black hole, it heats to extreme temperatures and emits X-rays. As these X-rays scatter through warped space-time and tangled magnetic fields, their polarization carries subtle signatures of the environment they pass through. If the black hole is spinning, space-time itself twists, imprinting a pattern on the escaping radiation. Recent advances have made X-ray polarimetry possible for the first time. Space-based instruments can now measure not just the energy and timing of X-rays, but the orientation of their electric fields. During brief flares near Sagittarius A star, these measurements could reveal how the inner flow of matter behaves and how fast the black hole is rotating. Spin is more than a technical detail. It is a record of history. A black hole that grew slowly by consuming gas from a disk may spin rapidly and align with its galaxy. One that grew through chaotic mergers may spin more slowly or tilt at odd angles. By measuring spin, astronomers can infer how Sagittarius A star came to be. Even as these tools advance, some questions remain forever beyond reach. The region inside the event horizon is sealed from the outside universe. Whether space ends in a singularity, rebounds in a quantum bounce, or opens into something entirely different, no signal can escape to confirm it. The interior remains a domain of theory and imagination. Yet this limitation has not stopped progress. By studying the boundary, the edge where information still flows outward, we have learned to turn indirect evidence into insight. The motion of stars, the shape of shadows, the flicker of flares, and the whisper of gravitational waves together form a picture that grows clearer with time. Sagittarius A star is not just an object at the center of the Milky Way. It is a natural laboratory where gravity, magnetism, and motion intersect under conditions found nowhere else. Each observation sharpens our understanding not only of black holes, but of the universe itself. As instruments improve and patience stretches across generations of scientists, the quiet heart of our galaxy continues to reveal its secrets, one subtle signal at a time. There is a deeper sense in which Sagittarius A star serves as a boundary, not only in space, but in understanding. It marks the point where familiar intuition gives way to abstraction, where everyday ideas about motion, time, and cause begin to lose their meaning. To approach it, even conceptually, is to confront the limits of what observation can tell us. Near the event horizon, time itself behaves differently. For an object falling inward, nothing unusual would seem to happen at the moment it crosses the boundary. Physics would appear normal, at least for a while. But to a distant observer, that same object would seem to slow, its light stretching toward longer wavelengths, fading until it vanished entirely. This disconnect between perspectives is not an illusion. It is built into the structure of spacetime. The event horizon divides not just locations, but possible histories. This strange behavior has led physicists to reconsider what information means in a universe governed by quantum rules. According to quantum mechanics, information cannot be destroyed. Yet classical descriptions of black holes suggest that anything crossing the event horizon is lost forever. This tension is known as the black hole information paradox, and it remains one of the most profound unresolved problems in modern physics. Some proposed solutions suggest that information is encoded on the event horizon itself, stored in subtle correlations on its surface. Others argue that information is carried away by Hawking radiation, the faint theoretical glow produced by quantum effects near the horizon over unimaginably long timescales. Still others propose that space-time itself must be redefined at the smallest scales, replacing the smooth fabric of general relativity with a more granular structure. While these ideas are highly theoretical, Sagittarius A star provides a real setting in which their consequences might one day be tested. If tiny deviations from expected behavior are observed near the event horizon, they could hint at how gravity and quantum mechanics are reconciled. Even a slight mismatch between prediction and observation would have enormous implications. Closer to home, the environment around Sagittarius A star continues to surprise. Despite its mass, the black hole wanders slightly, responding to the gravitational pull of surrounding stars. This subtle motion has been measured, confirming that the black hole truly dominates the central mass. Around it, stars form, live, and die in conditions unlike those found elsewhere in the galaxy. Some are massive and short-lived, suggesting that star formation can occur even under intense tidal forces. There are also clouds of gas on precarious paths, stretched and heated as they pass near the center. Each close approach becomes an experiment in real time, revealing how matter behaves under extreme gravity. Some clouds survive, others are torn apart, feeding the black hole in small, irregular bursts. These events remind us that Sagittarius A star is not isolated. It exists within a crowded ecosystem, shaped by and shaping its surroundings. The central region of the Milky Way is one of the most dynamic places in the galaxy, a crossroads where stellar evolution, gas dynamics, and relativistic physics intersect. As our understanding deepens, the language we use to describe this region continues to evolve. What began as a mysterious radio source has become a precise measurement of mass, motion, and geometry. What was once invisible is now outlined in detail. Yet the core remains dark, not because we lack imagination, but because the universe itself has drawn a boundary we cannot cross. Still, the pursuit continues. Each generation builds upon the last, refining instruments, extending observation times, and developing new ways to interpret subtle signals. Progress here is measured not in sudden breakthroughs, but in patience and accumulation. Sagittarius A star will not change dramatically on human timescales. Its story unfolds slowly across millions and billions of years. But our ability to read that story improves steadily. With every orbit tracked, every flare measured, and every wave detected, we move closer to understanding how gravity shapes the universe at its most extreme. At the center of the Milky Way, something unseen holds everything together. It does not announce itself. It does not demand attention. Yet by its quiet influence, It teaches us how to look deeper, think harder, and accept that some truths reveal themselves only indirectly. As this long exploration draws toward its horizon, Sagittarius A star remains what it has always been, a presence defined not by what it shows, but by what it shapes. It anchors the Milky Way quietly, without spectacle, influencing billions of stars through gravity alone. Unlike the blazing cores of distant galaxies, it offers no constant display. Its power is measured in patience rather than intensity. What makes Sagittarius a star remarkable is not just its mass or its location, but the way it allows us to study extremes without being overwhelmed by them. Because it is relatively calm, its surroundings are not drowned in radiation. This gives astronomers a rare opportunity to isolate individual processes, to observe how matter behaves when gravity is strong but not explosive, when magnetism competes rather than dominates, and when space-time curves gently enough to be measured with care. In this sense, the black hole at the heart of the Milky Way has become a reference point. By comparing it with more active black holes in other galaxies, scientists can begin to understand why some grow violent and luminous while others remain subdued. Differences in feeding rate, magnetic structure, spin, and environment all play a role. Sagittarius A star sits at one end of this spectrum, offering a baseline against which the extremes can be understood. Its story is also a reminder that the universe does not always reveal itself in dramatic flashes. Some of its most important truths are written slowly, traced in the steady motion of stars, in faint shifts of light, and in patterns that emerge only after decades of observation. The discovery of Sagittarius A star was not a single moment, but a gradual unveiling, each generation of instruments peeling back another layer of obscurity. From accidental radio noise to precise infrared astrometry, from blurred hints to a resolved shadow, the path toward understanding this object mirrors the broader progress of astronomy itself. Each advance depended not only on better technology, but on patience, collaboration, and the willingness to question assumptions. Even now, the black hole continues to challenge our understanding. It forces physicists to confront the limits of their theories and to reconcile ideas that work well separately but clash when combined. Gravity and quantum mechanics both succeed within their domains, yet near the event horizon they speak different languages. Sagittarius A star stands at that boundary, silently insisting that a deeper explanation exists. For those who study it, the black hole is not an ending, but an invitation. An invitation to refine models, to build better instruments, and to listen more carefully to the faint signals that carry meaning across the galaxy. It reminds us that absence can be as informative as presence, that darkness can be mapped, and that invisibility does not imply insignificance. At the center of our galaxy, something unseen continues its slow work, shaping orbits, bending light, and holding together the stellar city we call home. Long after individual stars have lived and died, long after civilizations rise and fall, Sagittarius A star will remain, a quiet constant in a changing universe. And by studying it, we learn not only about black holes, but about the nature of reality itself, how space and time respond to mass and motion, and how much of the universe can be understood without ever being touched, or seen. This is the heart of the Milky Way. Not a place of light, but a place of influence. Not a spectacle, but a lesson written in gravity. There is something uniquely fitting about the fact that the most massive object in the Milky Way announces itself so quietly. Sagittarius A star does not dominate the night sky. It does not glow, pulse, or blaze. Its presence is inferred through motion, through the steady curvature of orbits, through patterns that only reveal themselves when observed patiently over time. In many ways, it represents the opposite of how we often imagine cosmic power. For astronomers, this quietness has been a gift. A violently active black hole floods its surroundings with radiation, masking subtle effects and overwhelming delicate measurements. Sagittarius A star, by contrast, allows details to emerge slowly. Its environment can be studied layer by layer, from the broad motions of stars thousands of light-years away to the turbulent plasma swirling just outside the event horizon. Each region tells a different part of the story. The stars closest to the black hole act like test particles in a natural experiment. Their orbits trace the shape of space-time itself. Deviations from simple paths reveal relativistic effects, confirming predictions made over a century ago. These measurements do not rely on distant galaxies or abstract assumptions. They unfold in our own galactic neighborhood, close enough to be watched directly, year after year. Closer still, gas clouds and streams of plasma provide another perspective. As matter approaches Sagittarius A star, it heats, accelerates, and becomes threaded with magnetic fields. The radiation it emits carries information about temperature, density, and motion. Even brief flares, lasting only minutes, can reveal conditions just a few event horizon widths from the point of no return. Together, these observations form a layered map. Gravity dominates the large-scale structure. Magnetism shapes the flow at smaller scales. Relativity governs the paths of light and matter at the edge. Each physical law takes its turn, none operating in isolation. Sagittarius A star is not merely a black hole. It is a junction where multiple regimes of physics overlap. This is why it holds such importance beyond the Milky Way. The lessons learned here apply to black holes everywhere. Distant quasars, active galactic nuclei, emerging black hole pairs all operate under the same fundamental rules. By understanding the quiet case in detail, astronomers gain a reference point for interpreting far more extreme systems. There is also a philosophical weight to this object. Black holes challenge the idea that knowledge must come from direct observation. We cannot see inside the event horizon. We cannot sample its interior or send instruments across the boundary. Yet through inference, through consistency, and through careful measurement, we can describe it with remarkable confidence. The unseen becomes constrained by what it influences. This approach reflects a broader truth about science. Many of the most important structures in the universe are not directly observable. Dark matter reveals itself through gravity. Exopermits are detected through subtle stellar wobbles. The early universe is reconstructed from faint background radiation. Sagittarius A star fits into this pattern. It teaches us how much can be known without ever being touched. As technology advances, the picture will sharpen further. Future radio arrays will improve resolution, reducing uncertainty in images of the shadow. Polarization studies will map magnetic fields with greater clarity. Gravitational wave observatories will add an entirely new dimension, allowing us to sense motion rather than light. Each tool adds depth rather than replacement, building a more complete understanding. Yet no matter how detailed our observations become, a boundary will remain. The event horizon is not simply a technical limitation. It is a fundamental one. The universe itself enforces it. Beyond that line, cause and effect no longer connect to us. Information, in the ordinary sense, stops flowing outward. This is not a failure of instruments, but a feature of reality. And so Sagittarius A star occupies a special role. It is both accessible and inaccessible, close enough to study in extraordinary detail, yet sealed at its core. It invites investigation while withholding final answers. It stands as a reminder that understanding does not require total access, only consistent evidence and careful reasoning. At the center of the Milky Way, stars continue to orbit, gas continues to drift, and space-time continues to curve. The black hole does not rush. It does not need to. Its influence unfolds over millions of years, shaping the galaxy slowly and persistently. Long after individual stars burn out, long after spiral arms rearrange, Sagittarius A star will remain, anchoring whatever structure comes next. In studying it, we are not merely cataloguing an object. We are learning how the universe behaves at its most extreme, and how order can emerge even in places defined by collapse and darkness. The heart of the galaxy is not a place of destruction alone. It is a place of structure, balance, and quiet instruction. At this point in the journey, Sagittarius A star no longer feels like a distant abstraction. It becomes a fixed presence, something woven into the structure of the Milky Way itself. Every star in the inner galaxy responds to it. Every stream of gas is subtly guided by it, and even regions far beyond its direct gravitational reach carry the imprint of a galaxy that grew up around a central bowel. Anchor. One of the most remarkable aspects of Sagittarius A star is how ordinary its surroundings appear at first glance. The central region of the Milky Way is crowded, luminous, and chaotic, filled with stars of many ages and sizes. Massive blue stars burn brightly and briefly, while older red stars drift more quietly through the dense stellar environment. Supernova remnants expand, stellar winds collide, and clouds of gas compress and fragment. It is an active place, yet not one dominated by the black hole in any obvious visual sense. This apparent normality is deceptive. Beneath it lies a gravitational order imposed by the central mass. Stellar orbits are not random. They trace patterns shaped by a deep potential well. Over long timescales, this influence helps define the structure of the galactic bulge and stabilizes the motions within it. The black hole does not need to be active to be important. Its mass alone is enough. There is also a quiet symmetry to Sagittarius A star's role in the universe. Nearly every large galaxy appears to host a supermassive black hole at its center. This suggests that black hole formation is not an oddity, but a natural outcome of galaxy evolution. Wherever enough matter gathers, gravity finds a way to concentrate it further. In this sense, Sagittarius A star is not unique. It is representative. Yet it is precisely because it is representative and nearby that it matters so much. Other galactic centers are distant, blurred by space and time. Sagittarius A star is close enough for individual stars to be tracked, for flares to be watched as they rise and fall, and for relativistic effects to be measured directly. It is the only supermassive black hole whose influence we can observe with such intimacy. This closeness has reshaped our understanding of what black holes are and what they are not. They are not cosmic vacuum cleaners pulling everything inward indiscriminately. Most matter in the galaxy will never come near the event horizon. They are not agents of constant destruction. For long periods, they can remain almost dormant. Their true power lies in gravity's quiet persistence, not in dramatic displays. Sagittarius A star also challenges the way we think about scale. It is immense beyond human comprehension, yet small in astronomical terms. Its event horizon would fit comfortably within the orbit of Mercury. Its shadow, though the size of several suns laid side by side, appears vanishingly tiny from Earth. And yet, this small region governs the motion of stars across light years of space. Mass, not size, is what matters. In studying this object, astronomers have learned to be precise in ways that were once unimaginable. measuring motions to within a few kilometers per second at distances of tens of thousands of light-years. Detecting changes in brightness that last only minutes from an object we cannot see directly. Synchronizing telescopes across the planet to act as one. Each achievement reflects a growing ability to extract meaning from subtle signals. There is also a human story embedded here. The discovery of Sagittarius A star was not inevitable. It required curiosity, persistence, and often decades of work with no guarantee of success. Many of the most important insights came not from grand theories, but from careful measurement and the willingness to wait. The black hole revealed itself slowly, on its own terms. As future generations take over this work, they will inherit both the knowledge already gained and the questions that remain open. They will refine measurements, improve resolution, and perhaps uncover behaviors we have not yet imagined. Sagittarius A star will still be there, unchanged in any dramatic sense, yet offering new lessons as our perspective improves. In the end, the significance of Sagittarius A star is not confined to astrophysics. It speaks to a broader truth about the universe. That complexity can arise from simplicity, that invisible structures can shape visible worlds, and that understanding does not always come from direct access, but from careful attention to consequences. At the heart of the Milky Way, gravity writes its signature in motion and light. Sagittarius A star does not announce itself with brilliance. It reveals itself through influence. And by learning to read that influence, we have uncovered one of the deepest structures in our cosmic home. As our understanding deepens, Sagittarius A star begins to feel less like an isolated object and more like a crossroads where many branches of modern physics meet. It is here that gravity, motion, magnetism, radiation, and time itself are forced into close conversation. Each behaves as expected in isolation, yet near the galactic center, they overlap in ways that stretch intuition and test theory. One of the most profound lessons comes from how gently the black hole reveals itself. Nothing dramatic marks its presence. There is no obvious boundary, no visible surface, no warning sign in space. Stars orbit an empty looking point. Gas heats and cools. Light bends without announcing why. Only when these effects are traced carefully does the underlying cause become clear. This quietness is not a weakness of the system, but a gift to science. It allows processes to be observed without the overwhelming glare seen in active galaxies. Sagittarius A star has become a proving ground for general relativity. Einstein's equations make precise predictions about how spacetime should curve around a massive object. The precession of stellar orbits, the gravitational redshift of light, the size and shape of the black hole's shadow all follow those predictions closely. Each successful test strengthens confidence in the theory, while any deviation would hint at new physics waiting to be discovered. Yet general relativity is not the final word. It does not explain what happens at the singularity, nor how gravity fits with quantum mechanics. Sagittarius A star sits exactly where those unanswered questions become unavoidable. Matter falls in, information seems to vanish, and known laws reach their limits. Whatever the ultimate theory of nature turns out to be, it must explain objects like this. There is also a sense in which Sagittarius A star connects the past and future of the Milky Way. Its mass likely grew alongside the galaxy itself, increasing as stars formed, died, and recycled their material. In quiet epochs, it waited. In more active times, it likely flared, shaping its surroundings through radiation and outflows. Traces of those earlier phases may still be written into the structure of the central region. The stars closest to the black hole are messengers from that history. Their orbits encode information about past gravitational disturbances. Their compositions reflect the chemical environment in which they formed. Some may even be survivors of events where stars were torn apart or scattered by interactions near the center. Each orbit is a record, looping again and again through the same path, preserving evidence across centuries. From a broader perspective, Sagittarius A star reminds us that the universe does not privilege visibility. Some of the most important forces operate unseen. Dark matter shapes galaxies without emitting light. Black holes anchor them without revealing themselves directly. Even space-time itself is invisible, known only through its effects. Astronomy has become the art of studying what cannot be seen by watching how it acts. As instruments improve, the questions asked of Sagittarius A star will become more subtle. Instead of asking whether it exists, researchers now ask how its spin evolved, how its magnetic fields are arranged, how energy flows through its accretion environment, and how often it experiences bursts of activity. These are refinements, signs of a mature field pushing toward greater precision. The future promises even deeper insight. More sensitive telescopes will track fainter stars closer to the event horizon. Polarization measurements will map magnetic structures in detail. Gravitational wave observatories may one day listen to objects spiraling into the black hole, revealing its properties through ripples in space-time rather than light. Each new method adds a layer to the picture. Despite all this progress, Sagittarius A star retains its mystery. It cannot be approached, touched, or entered. It can only be inferred. And that limitation shapes the kind of knowledge we gain. It forces reliance on patience, inference, and humility. We learn not by intrusion, but by observation. In that way, the black hole at the heart of the Milky Way is also a mirror of scientific inquiry itself. It rewards careful attention, resists shortcuts, and reveals its secrets only gradually. It teaches that understanding often comes not from forcing answers, but from learning how to ask better questions. At the center of our galaxy, an unseen object continues its silent work. It bends space, guides motion, and anchors a vast system of stars. Sagittarius A star does not shine, yet it illuminates our understanding of the universe in ways few objects ever could. As observations continue, Sagittarius A star increasingly serves as a bridge between what we can measure and what we can only infer. It occupies a rare position in astronomy, close enough to be studied in detail, yet extreme enough to represent conditions found nowhere else in our galaxy. This balance has turned it into a natural laboratory, one where the universe allows experiments without interference. One of the most revealing aspects of this laboratory is time. Around Sagittarius A star, time behaves differently depending on where you stand. Close to the black hole, clocks would tick more slowly than they do far away, a consequence of intense gravity predicted by relativity. While no clock can be placed there directly, the effect is still measurable. Subtle shifts in the light from stars passing close to the black hole reveal that time itself is stretched. These measurements are not philosophical curiosities. They are physical confirmations that time and space are not fixed backgrounds, but dynamic participants in the universe. The motion of matter near the black hole also reveals a layered structure. Farther out, stars move according to relatively familiar gravitational rules. Closer in, gas behaves differently, heating, ionizing, and forming turbulent flows. Even closer, plasma dominates, guided as much by magnetic fields as by gravity. Each layer tells a different story, yet all are bound together by the same central mass. This layered environment explains why Sagittarius A star can appear calm while still being active at a fundamental level. Energy is constantly moving, being stored and released in small amounts. Magnetic fields twist and reconnect. Hotspots form briefly and vanish. Flares appear and fade. The system never truly rests, but it rarely erupts. It is dynamic without being destructive. Such behavior challenges simple categories. Sagittarius A star is neither fully dormant nor violently active. It occupies a middle ground that may be more common than once thought. Many galaxies may spend most of their lives in this subdued state, punctuated by shorter active phases triggered by mergers or sudden infalls of gas. If so, then the dramatic quasars seen in the distant universe may represent brief chapters rather than permanent conditions. Understanding this rhythm has implications beyond our galaxy. It helps explain how galaxies regulate themselves, how star formation can be encouraged or suppressed, and how matter is redistributed over cosmic time. The central black hole is not merely a passenger in this process. It participates, sometimes quietly, sometimes forcefully, shaping outcomes over billions of years. Sagittarius A star also reframes the concept of influence. Its gravity dominates the inner region, yet its reach fades with distance. Most stars in the Milky Way feel it only as a small contribution to the galaxy's overall mass. This reminds us that cosmic structures are hierarchical. Local forces matter most locally. Global structures emerge from the combined effects of many influences, not from a single dominating source. There is a certain elegance in this balance. The Milky Way is not ruled by its black hole in any absolute sense. Instead, the black hole is one component in a complex system, interacting with stars, gas, dark matter, and galactic dynamics. Its importance is undeniable, but it is not solitary. It is part of a larger pattern. As research continues, attention is increasingly turning toward long-term monitoring. Rather than isolated observations, astronomers now seek continuous records. Watching Sagittarius A star over decades reveals trends that single snapshots cannot. Slow changes in stellar orbits, gradual shifts in emission patterns, and rare but telling events all become meaningful when placed in a longer timeline. This long view aligns well with the nature of the object itself. Black holes evolve slowly. Their most dramatic changes unfold over timescales far longer than human lives. To understand them requires patience across generations. The scientists who began tracking stars near the galactic center did so knowing that they might not see full results within their own careers. Their work was an investment in the future. That investment has paid off. Each orbit completed, each flare recorded, each improvement in resolution has added clarity. Sagittarius A star has gone from a theoretical possibility to a well-characterized object, and now to a benchmark against which other black holes are compared. Yet even as knowledge accumulates, the sense of wonder does not diminish. If anything, it deepens. The more precisely the black hole is measured, the more striking its nature becomes. An object defined entirely by mass, spin, and charge, yet capable of shaping a galaxy. A region where familiar concepts dissolve, yet whose effects are felt across tens of thousands of light-years. At the heart of the Milky Way, Sagittarius A star continues its silent work. It does not announce the passing of time, but it marks it in orbits. It does not display its power openly, but it leaves signatures everywhere. And through careful observation, humanity has learned to read those signatures, slowly uncovering the story of the darkest place in our galaxy. As the picture becomes more complete, Sagittarius A star also reshapes how we think about certainty in science. Few objects have been inferred with such confidence from effects alone. No surface is seen, no interior sampled, no direct signal emerges from within. And yet the conclusion is firm. A supermassive black hole sits at the center of the Milky Way. Not because we wish it to be there, but because every independent line of evidence points to the same explanation. This convergence matters. Stellar orbits, radio emission, infrared flares, X-ray bursts, gravitational redshift, and now, direct imaging of the shadow, all align. Remove the black hole from the model, and the system stops making sense. Replace it with anything else, and contradictions appear. Density limits are violated. Orbits become unstable. Energy has nowhere to go. In this way, Sagittarius A star is not just a discovery, it is a solution that survived relentless testing. What remains uncertain is not its existence, but its details. How exactly matter flows in when feeding is weak. How magnetic fields organize themselves so close to the event horizon. How turbulence behaves when space-time itself is curved. These are not minor questions. They sit at the edge of known physics, where equations grow unstable and intuition fails. One of the more subtle insights from studying Sagittarius A star is how little it takes to maintain galactic order. The black hole does not dominate through violence. It does not constantly eject jets or flood space with radiation. Instead, its mass quietly deepens the gravitational well at the center, allowing stars to settle into long-lived configurations. In doing so, it contributes to the stability of the inner galaxy over billions of years. This challenges older assumptions that black holes must always be disruptive to matter and life. In reality, distance matters. The Milky Way's habitable regions lie far from the center, where the black hole's influence is diluted and indirect. Its calm state today likely contributes to the long-term stability of the galaxy, rather than threatening it. There is also a philosophical shift that comes from this understanding. Black holes were once seen as exotic curiosities, perhaps rare or pathological outcomes of stellar collapse. Sagittarius A star shows that they are foundational. Galaxies form with them, evolve with them, and likely cannot exist without them. The universe does not treat black holes as exceptions. It builds around them. As observation pushes forward, Sagittarius A star will remain central to testing new ideas. Alternative theories of gravity, modifications to general relativity, and quantum models of space-time all must confront the data coming from the galactic center. Any theory that cannot reproduce what we see there is incomplete. Future discoveries may refine the picture, but they are unlikely to overturn it. What will change is resolution, clarity, and depth. Images will sharpen. Motions will be tracked more precisely. Time variability will be resolved instead of averaged. The black hole will not become less mysterious, but its mystery will become more structured. In this way, Sagittarius A star embodies a broader truth about exploration. Understanding does not remove wonder. It redirects it. Each answered question exposes deeper ones. Each measurement opens new uncertainties. The dark center of the Milky Way remains dark, not because it is unknown, but because it represents the limit of what light itself can tell us. And so, at the core of our galaxy, something unseen continues to shape everything around it. It bends paths, slows time, organizes motion, and anchors a system of hundreds of billions of stars. It does all of this without spectacle, without sound, without light. Sagittarius A star is not a monster waiting to awaken. It is not a threat lurking in the dark. It is a fundamental feature of our cosmic home. A reminder that the universe is governed not only by what shines, but by what pulls. Not only by what we see, but by what we infer. At the very center of the Milky Way, gravity speaks softly. And by listening carefully, we have learned one of the deepest truths about the universe we inhabit. As this long arc continues, Sagittarius A star also reframes our sense of location. We often imagine ourselves living in a quiet corner of the universe, far from anything extreme. And in many ways, that is true. The Sun orbits safely in the outer regions of the Milky Way, far from violent radiation and dense stellar traffic. Yet the presence of the black hole reminds us that our galaxy is not a passive backdrop. It is an active structure with a deep, organized center. Every 230 million years, the Sun completes one orbit around that center. During all of human history, it has barely moved along that path. Civilizations have risen and fallen while the galaxy itself has remained essentially unchanged. Sagittarius A star has been there the entire time, quietly holding the inner regions together while the spiral arms turn like slow currents in a vast cosmic sea. This perspective places human time into sharp contrast with cosmic time. The processes shaping the galactic center unfold over millions and billions of years. Even the dramatic events, flares, stellar disruptions, mergers, are slow when measured against the lifespan of stars or galaxies. Sagittarius A star teaches patience by example. Nothing about it is rushed. Everything happens when gravity allows it to happen. It also teaches restraint. Despite its enormous mass, the black hole does not dominate everything around it. It allows stars to exist nearby. It allows complex structures to persist. It allows the galaxy to be more than a collapsed heap of matter. This balance between concentration and stability is one of the universe's recurring themes. Extremes exist, but they are often contained. From an observational standpoint, Sagittarius A star has forced astronomy to evolve. Many of the techniques now considered standard were refined or proven necessary because of this object. Long baseline interferometry, adaptive optics, precision astrometry, polarization mapping, and multi-wavelength coordination all reached new levels because the galactic center demanded them. In trying to understand one unseen object, scientists improved their ability to study the entire universe. There is also a quiet irony in how much effort has gone into imaging something defined by its invisibility. The famous ring images are not pictures of the black hole itself, but of light struggling at the edge of escape. What we celebrate in those images is not presence, but absence. A shadow, carefully outlined by what cannot survive near it. This inversion is important. It shows that knowledge does not always come from direct detection. Sometimes it comes from boundaries, from limits, from knowing where something must be, because nothing else can explain what happens nearby. Sagittarius A star is known not by what it emits, but by what it forbids. As future instruments come online, the relationship between observation and theory will tighten further. Measurements will no longer test whether general relativity works in this environment, but how precisely it works. Deviations, if they exist, will be small. Finding them will require extraordinary care. But those small deviations could point toward a deeper theory of gravity, one that unifies what currently remains separate. At the same time, Sagittarius A star will continue to anchor more speculative questions about information, about the ultimate fate of matter, about whether space-time itself has a smallest scale. These questions may never be answered through observation alone. But the black hole provides a real, physical context in which such ideas must operate. In that sense, Sagittarius A star is both an object and a boundary. It is something we study, and something that defines the limits of study. It marks the point where the universe allows us to observe up to a line, and no further. Everything beyond that line belongs to theory, mathematics, and imagination. Yet even with that limit, the influence of the black hole extends outward. Its presence is written into the motion of stars, the structure of the bulge, the behavior of gas, and the long-term evolution of the Milky Way itself. It does not need to be seen, to be central. It simply needs to exist. And so the story continues, not toward a dramatic conclusion, but toward deeper clarity. Sagittarius A star remains where it has always been. Silent, invisible, immense. And by studying it, we learn not only about black holes, but about how the universe builds order around emptiness, structure around darkness, and meaning from what cannot be touched. As we move further into this understanding, Sagittarius A star also reshapes how we think about centrality. Not just physical centrality, but conceptual centrality. It sits at the intersection of observation, theory, and limitation. It is where astronomy becomes less about cataloguing objects and more about interpreting consequences. There is something deeply instructive about the way this black hole governs without contact. Nothing needs to touch it for it to matter. Its gravity reaches outward, shaping motion long before any material ever approaches the event horizon. This distant influence is enough to organize the inner galaxy, to define stable paths, and to maintain coherence over immense spans of time. It is a reminder that the most powerful forces do not always announce themselves locally. Sometimes they operate through quiet reach. Sagittarius A star also emphasizes the difference between danger and drama. Popular imagination often portrays black holes as voracious destroyers, tearing apart everything nearby. In reality, the space around the galactic center is not a constant disaster zone. Stars live full lives there. Planets may form and persist. Even close to the black hole, stability exists as long as orbits are respected. Catastrophe is possible, but it is not the default. This distinction matters when thinking about the universe as a place where complexity can arise. Extreme objects do not automatically erase structure. They coexist with it. The Milky Way did not fail to become a spiral galaxy because of its black hole. It became one alongside it. This coexistence hints at a deeper harmony in cosmic evolution, where even the most extreme outcomes of gravity find a place within larger systems. Over time, Sagittarius A star has also changed how astronomers define success. Early questions were simple. Is there something massive at the center? Is it a black hole? Those questions have answers now. The modern questions are more refined. How steady is the accretion flow? How do magnetic fields regulate in fall? How often do small disruptions occur? These are questions of texture, not existence. They reflect a transition from discovery to understanding. The black hole's quietness has encouraged this shift. Because it is not constantly erupting, it allows small effects to be seen clearly. Subtle timing changes, weak flares, polarization shifts. All of these would be overwhelmed in a more violent system. Sagittarius A star is, in this sense, cooperative. It does not obscure itself behind excess brightness. It allows its physics to be studied piece by piece. There is also a broader implication for how galaxies live and age. If most supermassive black holes spend the majority of their time in low-activity states, then the dramatic quasar phase may be the exception rather than the rule. Galaxies might grow, evolve, and stabilize during long, quiet epochs, punctuated by brief but intense periods of activity. Sagittarius A star may represent the dominant mode, not the anomaly. This perspective reframes the distant universe. The brilliant quasars seen billions of light-years away may mark a youthful stage when galaxies were gas-rich and chaotic. Over time, as fuel is used or expelled, they settle into calmer states. The Milky Way, with its subdued center, may simply be older and more settled. Sagittarius A star could be a sign of maturity rather than inactivity. Looking inward from our position in the galaxy, this maturity offers a sense of continuity. The same object that shaped the early Milky Way still anchors it today. It will likely continue to do so for billions of years more. While stars come and go, while spiral arms shift and fade, the central black hole endures. Its changes are measured not in lifetimes, but in eras. This endurance invites reflection on permanence and change. Sagittarius A star is both stable and evolving. Its mass increases slowly. Its spin may change subtly. Its environment responds to long-term trends. Yet on any human timescale, it appears constant. This duality, slow change within apparent stillness, is one of the defining rhythms of the universe. And so, the black hole at the heart of the Milky Way becomes more than an object of study. It becomes a reference, a reminder that the universe operates on scales and tempos far beyond everyday experience. That understanding requires patience, and that some of the most profound structures reveal themselves only when we stop looking for spectacle and start paying attention to influence. At the center of our galaxy, Sagittarius A star continues to shape a vast stellar city without ever needing to be seen. Its presence is felt in motion, in timing, in curvature. And through it, we glimpse a universe that is governed not by noise, but by quiet, persistent force. As this journey approaches its later stages, Sagittarius A star begins to feel less like a distant object and more like a permanent feature of the cosmic landscape, something as fundamental to the Milky Way as the spiral arms or the halo of stars surrounding the disk. It is not simply located at the center, it defines what the center means. There is a subtle shift that happens when an object is studied for long enough. At first it feels mysterious, even alien. Over time, familiarity grows. Not because it becomes ordinary, but because it becomes integrated into our mental map of reality. Sagittarius A star has crossed that threshold. It is no longer just a theoretical solution or a suspected mass. It is a known presence, mapped, weighed, and monitored, even if it can never be seen directly. This familiarity has not removed the wonder. If anything, it has refined it. The questions are now quieter, more precise, more patient. Instead of asking what it is, we ask how it behaves when almost nothing is happening. We ask how it responds to the smallest changes in its surroundings. We ask how it remembers its past through spin, through alignment, through subtle structure in the space around it. There is also a growing awareness that Sagittarius A star may be one of the best natural laboratories available for testing the deepest ideas in physics. It is close enough to observe in detail, yet extreme enough to push theories to their limits. Few other objects offer that combination. Distant quasars are brighter but too far away. Stellar mass black holes are closer but lack the scale. Sagittarius A star occupies a rare middle ground. In that laboratory, gravity is no longer a gentle background force. It is the dominant architecture. Space and time are not passive stages but active participants. Orbits precess. Clocks run at different speeds. Light follows curved paths. All of this happens continuously, quietly, without spectacle. The universe demonstrates its most advanced physics not in explosions, but in steady motion. This realization has changed how astronomers think about observation itself. The goal is no longer just to detect signals, but to interpret patterns, to extract meaning from timing, polarization, and structure. Sagittarius A star has pushed astronomy toward a more holistic practice, where data from many wavelengths and techniques are woven together into a single narrative. There is also a philosophical dimension to this shift. A black hole represents an ultimate limit, a place where explanation ends and description must take over. We can describe what happens outside the event horizon with extraordinary accuracy. We can predict outcomes. We can test equations. But we cannot follow matter beyond that boundary. At that point, knowledge becomes indirect, inferred, constrained. Yet this limit does not feel like a failure. It feels like a boundary condition built into the universe itself. Sagittarius A star reminds us that not everything is accessible, not everything is observable, and that understanding does not require total access. It requires coherence. It requires consistency. It requires the ability to explain what can be seen without demanding what cannot. In this way, the black hole becomes a teacher. It shows how much can be learned without intrusion, how much structure exists even when the core is hidden. It demonstrates that absence can be as informative as presence, that shadows can carry as much meaning as light. As instruments improve, the image of Sagittarius A star will sharpen. Its ring will become clearer. Its magnetic patterns more defined. Its flares more precisely timed. Perhaps one day, motion will be visible, not just averaged away, but tracked in real time. Even then, the event horizon will remain a horizon, a line that cannot be crossed by information. And beyond that line, the universe keeps its secrets. Not out of cruelty, but out of structure. Sagittarius A star does not conceal itself intentionally. It simply exists according to the rules of space-time. Those rules allow us to observe up to a point and no further. From our quiet vantage point, orbiting far from the galactic center, this is enough. The black hole does not need to be revealed completely to be understood meaningfully. It has already taught us about gravity, motion, time, and scale. It has already reshaped astronomy. It has already anchored our galaxy for billions of years. In the end, Sagittarius A star is not a monster waiting to awaken, nor a mystery waiting to be solved once and for all. It is a constant, a silent presence at the heart of the Milky Way. And through steady observation, careful theory, and patient curiosity, it continues to show us how the universe holds itself together around something we can never see. As this long view settles, Sagittarius A star also reframes how we think about endings, not as abrupt conclusions, but as transitions stretched across unimaginable spans of time. Black holes are often described as final states, the end point of collapse, where matter and light vanish from the story. Yet Sagittarius A star shows that an ending can also be a beginning, a structure around which everything else continues to evolve. Nothing about the galactic center feels hurried. Even the most dramatic future events unfold slowly. When the Milky Way eventually merges with Andromeda, the process will take hundreds of millions of years. The central black holes will not rush toward each other in a sudden crash. They will spiral together gradually, orbit after orbit, releasing energy in the form of gravitational waves long before their final union. Sagittarius A star will spend much of that time doing what it has always done, responding to gravity and momentum with quiet inevitability. In that far future, the black hole may finally experience a sustained period of activity again. Vast amounts of gas and dust stirred up by the merger could funnel inward, lighting the core of the newly formed galaxy. For a time, the center might blaze like a quasar, visible across intergalactic distances. But even that phase will be temporary. Activity will peak and fade, and the merged black hole will settle once more into a long, dim existence. This cycle, growth, activity, quiet, is not unique to Sagittarius A star. It appears to be the life pattern of supermassive black holes throughout the universe. They are not constantly destructive or luminous. They are episodic. Their influence comes in waves, separated by long intervals of calm. Understanding this has helped astronomers reinterpret observations of distant galaxies, recognizing that a quiet core today may have been violently active in the past. There is a deeper lesson here about scale and perspective. Human intuition struggles with durations measured in millions of years. Yet for galaxies and black holes, such times are brief. The current quietness of Sagittarius A star may feel permanent to us, but it is likely just one chapter in a very long narrative. The same object that seems dormant now may one day dominate the energy output of the galaxy again. At the same time, Sagittarius A star emphasizes how little direct influence such an awakening would have on life far from the center. Even if it entered a bright active phase, the vast distances involved would protect most of the galaxy. Radiation weakens with distance. By the time any outburst reached the region of the Sun, it would be diluted, scattered, and largely harmless. The universe allows violence and stability to coexist without constant conflict. This coexistence reinforces the idea that black holes are not cosmic villains. They are natural outcomes of gravity operating over long periods. They recycle matter. They redistribute energy. They shape environments without needing to dominate them continuously. Sagittarius A star has likely consumed countless stars over its lifetime, yet the galaxy remains rich, structured, and full of ongoing star formation. As observations continue, Sagittarius A star will remain a focal point, not because it changes dramatically, but because it does not. Its steadiness allows comparison. Its predictability allows precision. Each small deviation from expectation becomes meaningful precisely because the background is so stable. In this way, the black hole at the center of the Milky Way serves as both an anchor and a reference. It grounds our understanding of galactic dynamics while pointing toward the deepest questions about gravity and spacetime. It reminds us that the universe operates according to principles that are consistent, even when their outcomes feel strange. And so, as this exploration gradually slows, Sagittarius A star remains where it has always been. Not as a dramatic finale, but as a quiet constant. A presence that does not demand attention, yet rewards it. A reminder that the universe is not built around spectacle alone, but around balance, patience, and the slow unfolding of structure over time. As the final stretch of this journey comes into view, Sagittarius A star also invites a gentler way of thinking about the universe itself. Not as a place of constant upheaval, but as a system that favors equilibrium over excess. Even its most extreme objects spend most of their existence in quiet balance. The dramatic moments, the flares, the mergers, the bursts of radiation are brief punctuation marks in a much longer, calmer sentence. There is something almost reassuring in that. The universe is capable of immense violence, yet it does not rely on it. Structure emerges not from chaos alone, but from stability sustained over time. Sagittarius A star exemplifies this principle. It holds the Milky Way together not through constant activity, but through steady presence. From our distant vantage point, the black hole will never feel close. It will never dominate the night sky. It will never intrude directly into daily experience. And yet, it is part of the reason our galaxy has the shape it does, the reason the inner stars move as they do, the reason the Milky Way has a coherent heart rather than a scattered core. Influence does not require proximity. It requires persistence. This idea echoes throughout modern astrophysics. Many of the most important forces in the universe operate quietly. Dark matter shapes galaxies without shining. Dark energy drives cosmic expansion without revealing its nature. Even gravity itself is subtle on small scales, noticeable only when mass accumulates over great distances. Sagittarius A star belongs to this family of silent architects. As instruments become more sensitive, future astronomers will likely uncover finer details in the region around the black hole. Small oscillations in the accretion flow, shifts in magnetic alignment, patterns that repeat over long timescales. Each of these will add resolution not just to images, but to understanding. The story will become sharper, but not louder. There may also come a time when Sagittarius A star surprises us. A sudden increase in activity, a rare event involving a massive star, a long-predicted merger finally beginning. If that happens, it will be studied with an array of tools that did not exist when the black hole was first suspected. Gravitational wave detectors, polarimetric telescopes, interferometers spanning Earth and space. The quiet object will briefly become a focal point of cosmic attention. And then, inevitably, it will quiet again. This rhythm, attention followed by stillness, mirrors the way we learn. Periods of discovery followed by long spans of refinement. Sagittarius A star has already transformed astronomy once. It will likely do so again, not through constant change, but through the depth of what it allows us to test. In the broader sweep of cosmic history, the black hole is neither beginning nor end. It is a middle structure, a stable node through which matter passes, energy is redistributed, and information is transformed. The galaxy did not start with it, and it will not end with it. But throughout much of its life, Sagittarius A star will remain central. As this exploration draws closer to rest, the image that lingers is not one of destruction or mystery alone, but of quiet order, a massive object, invisible by nature, shaping a galaxy through patience rather than force. A reminder that the universe often works best when it is not trying to be seen. At the heart of the Milky Way, beyond dust and distance, Sagittarius A star continues its long watch. Silent, enduring, and essential to the story of the galaxy that slowly turns around it. As the journey reaches its natural resting point, Sagittarius A star settles back into its true role, not as a spectacle, but as a reference point for understanding how the universe holds together over deep time. It does not demand attention. It does not announce itself. Yet its influence is woven quietly into the structure of the Milky Way, present in every long orbit, every stable path, every slow turn of the galactic disk. What makes Sagittarius a star so compelling is not what it does, but how consistently it does it. For billions of years it has remained where it is, responding only to gravity and momentum, growing slowly, shaping subtly. While stars are born and die, while spiral arms shift and blur, the black hole endures. It is one of the most stable features in a galaxy defined by motion. This endurance reframes our sense of permanence. Mountains erode. Oceans rise and fall. Stars exhaust their fuel. Even galaxies collide and transform. Yet some structures persist across eras that dwarf all others. Sagittarius A star is one of those structures. It exists on a timescale where change is measured not in events, but in epochs. In that sense, it becomes easier to understand why black holes occupy such a central place in modern cosmology. They are not merely exotic objects. They are anchors. They represent the long-term outcome of gravity, doing its work patiently and completely. They show what happens when mass concentrates, energy redistributes, and time stretches into something almost unrecognizable. For observers far from the galactic center, Sagittarius A star will always remain abstract. A mass inferred from motion. A shadow outlined by light. A presence confirmed through consequence. And that is enough. The universe does not require proximity to be meaningful. It allows understanding to emerge from distance. As technology advances, the picture will sharpen. The ring will clarify. The environment will reveal finer structure. Perhaps motion will one day be traced in detail, showing matter circling the event horizon before slipping away. Even then, the core truth will remain unchanged. There will always be a boundary beyond which observation cannot pass. That boundary is not a flaw in knowledge. It is a feature of reality. Sagittarius A star reminds us that the universe is not built for complete access. It is built with limits, horizons, and edges that define where understanding transitions into inference. Within those limits, however, an extraordinary amount can be learned. And so, at the center of our galaxy, the black hole remains. Not awake or asleep, not active or dormant in any human sense. Simply present, holding space and time in gentle curvature, guiding stars along invisible paths, shaping a vast stellar system without ever needing to be seen. The Milky Way turns. The stars move. And at the quiet heart of it all, Sagittarius A star continues its patient existence, a silent constant in a universe defined by motion. As the final layers settle, it becomes clear that Sagittarius A star is best understood not as an object we observe, but as a condition that shapes everything around it. Its gravity defines what is possible in the inner galaxy. Its presence sets the scale for motion, energy, and stability. Even when nothing dramatic is happening, it is still doing its work, quietly and continuously. There is a tendency in science communication to focus on moments of revelation. The first detection, the first image, the sudden flare. But the deeper truth of Sagittarius A star lies in what happens between those moments. In the long stretches of apparent inactivity where equations hold, orbits repeat, and predictions remain reliable. These intervals are not empty. They are the foundation that makes interpretation possible. This is why the black hole has become such a powerful reference point in modern astrophysics. When something unusual is observed near the galactic center, it stands out precisely because the background behavior is so well understood. Small deviations carry meaning. Slight shifts matter. Sagittarius A star has allowed astronomy to become more precise by being so consistent. It has also reshaped how scientists think about visibility. The most important structure in the Milky Way cannot be seen directly in any wavelength. It reveals itself only through influence. This inversion challenges a deeply human instinct to equate seeing with knowing. Sagittarius A star shows that understanding can emerge from absence, from shadow, from the way light fails to return. That lesson extends beyond black holes. Much of the universe operates through hidden frameworks. Dark matter scaffolds galaxies. Fields shape particles. Curvature guides motion. The visible universe rides on top of invisible structure. Sagittarius A star is one of the clearest examples of this principle made real. As the future unfolds, this hidden structure will become increasingly accessible through indirect means. Polarization maps will trace magnetic geometry. Timing arrays will reveal gravitational ripples. Long baseline interferometry will resolve motion on scales once thought impossible. None of these will show the black hole itself, but all of them will deepen our understanding of its surroundings. Even then, the event horizon will remain what it has always been, a one-way boundary, not because nature is withholding information, but because space-time itself is arranged that way. Sagittarius A star is not secretive. It is simply consistent with the rules that govern everything else. In the end, the black hole at the center of the Milky Way becomes a reminder of how the universe balances mystery and order. There are regions we cannot explore directly, yet there is enough structure around them to build reliable knowledge. There are limits, but those limits are stable. They do not shift arbitrarily. They allow science to proceed with confidence up to the edge. And so, as this exploration stretches gently onward, Sagittarius A star remains unchanged in its essence. It does not demand resolution. It does not offer closure. It exists as a steady presence around which understanding continues to orbit. At the quiet heart of our galaxy, beyond dust and distance, gravity curves space-time into a shape that holds everything together. And in that curvature, the story of the Milky Way continues, slow, ordered, and vast, guided by something we can never touch, yet cannot ignore. As the narrative extends a little further, Sagittarius A star begins to feel less like a destination and more like a horizon that our understanding slowly approaches without ever crossing. Each improvement in observation brings us closer, sharpening detail, reducing uncertainty, yet always stopping just short of the core itself. This asymptotic approach is not frustrating. It is defining. It shapes how knowledge grows around objects governed by extreme gravity. There is a quiet elegance in this process. Science advances not by overturning everything at once, but by narrowing what remains unknown. With Sagittarius a star, the unknowns have become finely bounded. We know its mass with remarkable precision. We know its location to extraordinary accuracy. We know how nearby stars respond to its pull. What remains uncertain now is not whether it exists or what it is in broad terms, but how subtle processes unfold in its immediate vicinity. This shift from certainty to refinement is one of the clearest signs of scientific maturity. Early astronomy asked where things were. Modern astronomy asks how they behave under conditions that test the limits of theory. Sagittarius A star has helped drive that transition. It has turned the galactic center into a proving ground, where ideas about space-time, magnetism, and energy flow must survive contact with reality. It has also changed how we think about scale in the universe. The black hole is enormous by any human standard, yet on the scale of the galaxy it occupies a region smaller than a single star's orbit. On the scale of the universe, even the Milky Way itself is just one structure among hundreds of billions. Sagittarius A star sits at the intersection of these scales, reminding us that influence does not depend on size alone, but on position and context. From this perspective, the black hole is not an isolated anomaly. It is part of a broader pattern. Most large galaxies appear to host similar central objects. They grow with their galaxies. They evolve alongside them. Sagittarius A star is not special because it exists, but because it is close enough to study in detail. It is our local example of a universal phenomenon. That closeness has allowed astronomers to move beyond snapshots and into long-term monitoring. Decades of observation have built a record of motion, brightness, and variability. This temporal depth is rare in astronomy. Few objects can be watched evolve, even subtly, over a human lifetime. Sagittarius A star offers that opportunity, not through dramatic change, but through steady accumulation of data. Over time, this record will become even more valuable. Patterns that are invisible in a single year may emerge across generations. Cycles may reveal themselves. Small trends may become clear. The black hole will not suddenly transform, but our understanding of it will continue to deepen as patience compounds into insight. In this way, Sagittarius A star stands as an example of how the universe rewards sustained attention, not with spectacle, but with coherence, not with final answers, but with increasingly precise questions. It shows that some of the most meaningful discoveries arise not from chasing novelty, but from returning again and again to the same quiet place and noticing what has always been there. And so the journey does not end with resolution, but with continuity. The black hole remains. The galaxy turns. Observation continues. Understanding grows slowly, guided by the steady influence of something that cannot be seen, yet shapes everything around it. At the center of the Milky Way, Sagittarius A star persists, not as a mystery waiting to be solved once and for all, but as a constant presence that invites endless, careful attention and rewards it with a deeper sense of how the universe holds itself together. As this exploration stretches a little further, Sagittarius A star also reframes how we think about significance. In everyday terms, importance is often tied to visibility, to brightness, to activity. Yet the most influential object in the Milky Way is neither bright nor loud. It does not dominate the sky. It does not announce itself. Its importance comes from position and inevitability, from the way gravity accumulates consequences over time. This inversion challenges intuition. We expect power to be obvious. Sagittarius A star shows that power can be quiet, persistent, and structural. It does not act through bursts alone, but through the steady shaping of paths. Stars do not feel its pull as a dramatic force, but as a rule that defines where they may go and how fast they may travel. In this way, the black hole acts less like an engine and more like a framework. That framework has allowed the inner galaxy to remain coherent for billions of years. Without a central mass of this kind, the motions of stars near the core would be far more chaotic. Orbits would overlap and destabilize. Structures would dissolve more easily. Sagittarius A star provides a gravitational anchor that gives order to what would otherwise be a turbulent region. It is not the only contributor to stability, but it is a crucial one. There is also something instructive about how indirect our relationship with the black hole remains. Everything we know about it comes from observing what it influences, never from observing it directly. This has forced astronomy to become more careful, more inferential, more precise. It has sharpened methods. It has strengthened theory. In learning how to study Sagittarius A star, scientists learned how to extract meaning from absence itself. This skill has proven essential elsewhere. The same reasoning underpins the study of dark matter, exoplanets, and the large-scale structure of the universe. In many cases, the most important components are invisible. Their existence is revealed through motion, imbalance, or curvature. Sagittarius A star is one of the earliest and clearest demonstrations of this principle at work. As future generations continue this work, the black hole will remain a stable reference against which change can be measured. New stars will be discovered. New instruments will refine measurements. New theories may alter interpretation. Yet the central mass will still be there, responding to gravity as it always has. Its consistency will allow new ideas to be tested without ambiguity. There is also a quiet humility built into this story. No matter how advanced our tools become, there will always be a region beyond reach. The event horizon is not a technical limitation. It is a physical one. Sagittarius A star teaches that the universe includes boundaries that cannot be crossed by information, no matter how sophisticated the observer. Understanding must adapt to those boundaries rather than attempt to erase them. In that adaptation, science becomes less about conquest and more about coherence. The goal shifts from seeing everything to explaining what can be seen in a way that remains internally consistent. Sagittarius A star fits perfectly into this mode of understanding. It offers enough access to be studied rigorously, and enough inaccessibility to remain fundamentally profound. And so, as this long narrative continues to unfold, the black hole remains what it has always been. Not a threat, not a spectacle, but a structural truth at the heart of the Milky Way. A reminder that the universe does not need to be dramatic to be meaningful, and that some of its deepest insights emerge from quiet, patient attention to what shapes everything else, without ever stepping into the light. As the closing arc begins to take shape, Sagittarius A star invites one final shift in perspective, away from objects and measurements, and toward process. What we are really studying at the galactic center is not just a black hole, but the long-term behavior of gravity itself when it is allowed to act without interruption for billions of years. Gravity is often treated as the simplest of forces, predictable, conservative, almost dull compared to electromagnetism or nuclear interactions. Yet near Sagittarius A star, gravity reveals its full depth. It curves space-time. It alters time itself. It dictates which futures are possible and which are not. In this environment, gravity is no longer just a background rule. It is the primary author of structure. What makes this especially striking is how stable that authorship has been. The Milky Way has undergone mergers, starbursts, and long periods of calm. Gas has flowed inward and outward. Stars have been born, migrated, and destroyed. Through all of this, Sagittarius A star has remained dynamically central. Its mass has grown, but its role has not changed. It continues to define the deepest well in the galaxy's gravitational landscape. This constancy allows astronomers to think of the black hole as a kind of fixed point in an otherwise evolving system. By measuring how stars, gas, and radiation behave relative to it, researchers can disentangle complex processes that would be far harder to interpret elsewhere. The galactic center becomes a reference frame for understanding motion, energy, and stability on the largest scales. There is also a subtle emotional shift that comes with this understanding. Early discussions of black holes were often framed around fear or destruction. They were cosmic traps, regions of no return. Sagittarius A star softens that narrative. It shows that a black hole can exist quietly at the heart of the living galaxy, without rendering that galaxy hostile or unstable. It reframes black holes as participants in cosmic ecosystems, rather than endpoints of catastrophe. This reframing matters because it aligns black holes with the rest of astrophysics. Stars burn fuel and die. Galaxies form, merge, and settle. Black holes grow, flare, and quiet. None of these processes exist in isolation. Sagittarius A star is not an aberration. It is one expression of how matter behaves when gravity is given enough time and enough mass to work with. As this perspective settles, the black hole becomes less alien. It remains extreme, but it no longer feels out of place. It belongs to the same universe that produces stars, planets, and life. Its physics may be unfamiliar, but its role is coherent. It is part of a continuous story, rather than a rupture in it. Looking ahead, future observations will not radically redefine what Sagittarius A star is. Instead, they will refine how precisely we understand its behavior. Margins of error will shrink. Models will sharpen. Competing theories will be tested more rigorously. The black hole itself will remain unchanged by this scrutiny. It will simply continue to exist, responding only to gravity, momentum, and time. This asymmetry is important. The object does not adapt to our understanding. Our understanding adapts to the object. Sagittarius A star does not reveal itself willingly or reluctantly. It follows physical law without regard for observation. That impartiality is part of what makes it such a powerful scientific anchor. And so, as this second-to-last passage settles, the black hole stands not as a mystery waiting for a final answer, but as a structure that supports endless refinement, a place where certainty and uncertainty coexist in stable balance, a reminder that knowledge can deepen indefinitely even when access is limited. At the center of the Milky Way, gravity continues its work, uninterrupted, unobserved in its core, yet unmistakable in its effects. And around that quiet center, understanding continues to orbit, slowly, patiently, drawn inward by curiosity rather than force. As the journey comes gently to rest, Sagittarius A star remains exactly where it has always been, not as a conclusion, but as a constant presence around which everything else continues to move. There is no final revelation waiting at the center, no moment when the universe suddenly explains itself. Instead, there is continuity. Gravity persists. Orbits repeat. Time stretches forward without urgency. What makes this ending feel complete is not that every question has been answered, but that the shape of the unanswered questions is now clear. We know where the limits are. We know which boundaries cannot be crossed by light or information. And within those boundaries, we have learned how much can still be known. Sagittarius A star teaches that understanding does not require dominance over nature. It requires alignment with it. The black hole does not yield its secrets through force or intrusion. It yields them through patience, precision, and respect for the rules that govern spacetime itself. This approach has reshaped astronomy, turning it into a science of inference as much as observation. There is also a quiet sense of proportion that emerges when thinking about the galactic center. Human concerns operate on timescales of years and generations. Even stellar lifetimes feel vast by comparison. Yet Sagittarius A star exists on a scale where entire civilizations would rise and vanish without leaving a trace. It anchors the Milky Way across epochs so long that change becomes almost abstract. And still, this immense structure is part of the same universe that gives rise to small things. Atoms, cells, minds capable of curiosity. The same physical laws that govern the event horizon also govern the motion of planets and the chemistry of life. Sagittarius A star is extreme, but it is not separate. It belongs to the same coherent reality as everything else. This coherence is perhaps the most comforting lesson of all. The universe is not stitched together from incompatible pieces. Its most violent and most delicate phenomena arise from the same underlying principles. Black holes do not break the rules. They reveal how the rules behave under the most demanding conditions. At the heart of our galaxy, Sagittarius A star continues to curve space and time without intention or awareness. It does not watch the stars orbit it. It does not know the galaxy exists. And yet, through its mere presence, it shapes an entire stellar system. Influence does not require awareness. It requires consistency. From our distant position in the Milky Way, we will never experience the black hole directly. We will only ever know it through motion, shadow, and delay, through light bent around absence, through stars that move as if guided by something unseen. And that is enough. Because in learning to understand Sagittarius A star, we have also learned how to understand the universe on its own terms. Slowly, indirectly, with humility toward limits and confidence in patterns. The black hole has not just deepened our knowledge of gravity, it has refined our relationship with the unknown. And so the story does not end with a revelation, but with equilibrium. The Milky Way turns. The stars continue their long paths. Time advances without pause. And at the quiet center of it all, beyond dust and distance, Sagittarius A star remains, invisible, immense, and unwavering, a silent anchor in a moving galaxy.